are big, massive conglomerates of spheres of hydrogen gas, plus other elements are, in trace only, except helium, which is there by almost 24% by mass, of 24% by mass of helium is there. So hydrogen, helium, and the other elements. So you can see spectral lines. And these people, in taking the spectra of galaxies, noticed that the spectral lines were looking shifted. So they calculated the redshift. Most of the galaxies appeared to be having their spectral lines shifted to the longer wavelength side. And in VIBGYOR, the rainbow, red side is the longer wavelength side. So these shifts are usually associated with cosmology. They are usually called redshifts. What they found was that when they plotted this redshift, if you assume that it is due to Doppler effect, the redshift can be converted to a velocity V is equal to C into Ez, where Ez is delta lambda by lambda. When they plotted velocity versus distance, which is the plot of these small black dots which you see at the bottom of the slide, they found that V is proportional to D, and you can write V is equal to HT. So since these are redshift, it's also these galaxies, these sources of light are moving away from us. It is called the Hubble-Lamaithe law. The V is equal to HT. How do you interpret it? So this is the beginning of what is called the Big Bang cosmology. This can be very easily interpreted as we are living in an expanding universe. If you take a rubber band and put equally spaced dots on it and stretch the rubber band, suppose you are standing on one point, the dot 1 centimeter away will appear to move away from you with some speed, depending on the speed, on how fast you are stretching the rubber band. But if you look at the dot which is 2 centimeters away from you, you find that the dot 2 centimeters away is running away from you, will appear to run away from you at double the speed of the dot at 1 centimeter. So the speed of recession will appear to be proportional to the distance if you are living in an expanding universe. So Hubble's law is interpreted in that fashion. So you get an expanding universe idea. Now, if we are living in cannot be the electromagnetic force because matter in the bulk is electrically neutral. The strong and the weak forces are dominant only in subnuclear scales. The only force left is gravitation. And gravitation is known to be always attractive. So if you're living in a universe which appears to be expanding and gravitation is always attracting, it means the universe must have started this expansion with an explosion, that it was given some amount of expanding kinetic energy. It started off expanding like that. So this gave the idea of the Big Bang. This explosion is called the Big Bang. So you have Big Bang cosmology. Now, before we go to the next aspect of Big Bang cosmology, let us look at the right side of the slide. I have written there standard candles. To find distances in the universe, if you supernovae provide you with what are called standard candles, they are white dwarf stars which sort of cross the Chandrasekhar limit and explode. You see a light curve, the amount of light emitted is on the y-axis, time is on the x-axis. You see that the light from the supernova, as it explodes, it increases in brightness, goes to a peak and then decreases. This peak brightness is a constant for type 1a supernovae. So type 1a supernovae can be used as standard candles, and a given supernova is almost as bright as a whole galaxy. The amount of light of a whole galaxy concentrated at a point. So they can be seen to very far distances. So you can find distances in the universe using supernovae as standard candles. Supernova cosmology it is called. So let us look at the next thing. So what are we talking about when we say the universe? The contents of the universe, what are they? Us, we are there. So we are still not in a position to explore the universe and immediately come to produce human beings. Life, yes, a detail. Eventually, we expect to put them in. Planets, a detail eventually. Stars, a very important detail eventually. Galaxies, a very significant detail because it is allowing you to track what the universe is doing. With these contents, more contents will come later. And you assume, wherever you look, the universe sort of looks the same. In whichever direction you look, the universe looks the same. That is homogeneity, isotropy, plus fully homogeneous, fully isotropic, but quantum theory tells you that you have the quantum fluctuations. You have the uncertainty principle. Nothing is perfect. There will be fluctuations in the system. So you have these fluctuations. This will be the minimal assumptions with which we can start our cosmology. homogeneity, isotropy, plus these quantum fluctuations. Now, what are the contents again? Let us look. We have matter, all these quarks and leptons, fermions. Mainly we notice light when you are thinking about the cosmos. And there is the space-time. So matter, are fermions, the quarks and leptons, light, bosons. But what about space-time? We don't have much idea. We have in quantized gravity. We think of it as space-time only. These fermions, quarks and leptons, bosons, the gauge bosons of the standard model, then the Higgs boson, and then space-time. You don't know. You have space-time and that's it. We can determine the average mass per energy or energy per unit volume of the universe. The average give you what is the smooth, if you assume on large scales, you can assume that it is smooth. You can look at the behavior of this smooth quantity, the averaged mass and energy density. How is it evolving with respect to time? For us, evolution is always connected with time. Then what you can do is, you look at the fluctuations on this smooth distribution of matter or light or even space-time, gravitational waves. You can see what is the distribution. In statistics, since these are fluctuations, varying things, you can look at its distribution. We can look at various aspects connected with the statistics of these random distributions of over and above the mean. So you can study this distribution. You can study the evolution of both the mean as well as the fluctuations. That is what you can do with the universe. So let us see. How do you proceed? We're told gravitation is the dominant force, and the best theory we have for gravitation is the general theory of relativity, plus the idea of homogeneity, the isotropy, and cosmological time. That is, there is a uniform flow for time throughout the history of the universe, and this flow, it's the same for all observers anywhere in the universe. With these three assumptions, we write down something called the Friedmann-Lemaitre-Robertson-Walker metric. Now, what is a metric? Let's go to, we have given the form here. Let us go to the next slide. Look at the bottom portion of the next slide. On the right side, I have written square of the distance is equal to dx square plus dy square plus dz square. This is very, very familiar to you from Euclidean geometry. This is the expression of Pythagoras theorem for the diagonal of a cube of side dx, dy, dz. Now, you've already studied about special theory of relativity. When you go to special theory of relativity, you have pseudo-Euclidean geometry with time intervals also entering. I haven't written it down here. Then the interval which you notice, which doesn't change between inertial observers. Any two inertial observers will measure the same ds square. In the case of non-relativistic physics, the interval which doesn't change between observers is ds square is equal to dx square plus dy square plus dz square. Time is the same for everybody when you don't have relativity anyway. When you go to special relativity, you have ds square is equal to c square dt square minus dx square minus dy square minus dz square. Now, when you go to general theory of relativity, you cannot have a Euclidean type geometry anymore. Space is time gets curved. So instead of, if you think of dx square as dx dx, then you can think of dx 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 dy dy dz etc. In concise notation, this is written as dxi dxk. ds square, the interval will become gik, where the gik are functions of the coordinates into dxi dxk. In the repeated indices I and k, there is summation. You will write the metric like that. That is, metric means something which allows you to measure the separation between 2 points whose coordinates are xi and xi plus dxi, the I running from 0, 1, 2, 3. 0 is time, 1, 2, 3, xy, z, let us say. So this is the metric which captures the curvature of space-time. And what does general relativity say? General relativity tells you to think of, instead of the force, it says if there is matter energy, space-time is curved. And what does matter energy do? It follows the shortest length paths in the curved space-time. This describes the motion of the mass as well as the apparent, what we think is the force felt by the mass. So here is what is written, the Friedmann-Lemaitre FLRW metric. So the GIK will have one unknown function sitting there, the a square of t. A is a function of time alone. So this is a metric which captures homogeneity, isotropy, and a universal flow of time for everybody anywhere in the universe. So with this metric, now what do we need to know? We need to know what the universe is doing. What is the happening to this metric? So the evolution of the universe, its expansion, etc., will be captured by this scale factor, this A of t, which is sitting in this metric, which is called the scale factor. So we want the equation of motion, like we write F is equal to ma, we want the equation of motion. In general theory of relativity, the equation of motion is given by the Einstein equation, which is written here. GIK is called the Einstein tensor. It captures the curvature of space-time. On the other side, we have 8 pi g by c raised to 4. G is Newtonian constant of gravitation, and TIK is the energy momentum tensor. Energy momentum tensor is sitting there because both the matter as well as energy contributes to gravitation. So it's a cause-effect relation like any other equation of physics. The cause is matter energy, the effect is the curvature. So it relates cause and effect like this. So I have written the expression GIK in terms of what is called the Ricci tensor and the Ricci scalar. The Ricci tensor is written in terms of the Riemann tensor. The Riemann tensor is written in terms of the Christoffel symbols. The Christoffel symbols may be written in terms of the metric tensor. And the metric tensor, we have got the FLRW metric for a homogeneous isotropic universe with a cosmological time. So if you substitute that metric and write down this equation, and in addition, we have to put in a TIK. What about the matter energy? We put in a matter energy for, we have got a diagonal form for the metric. If you use, let us say, spherical polar coordinates, type coordinates, for example, the 0, 0 component, it's a diagonal F. That's why diag is written there. Rho is the 0, 0 component. Then the 1, 1, 2, 2, and 3, 3 components are minus P, minus P, minus P, where P is the pressure. You substitute TIK for this for TIK and the FLRW metric for GIK and write down the Einstein equations to get this set of differential equations for the unknown function A of t sitting in the metric. These equations are called the Friedmann equations. So when you solve this, we get the behavior of the scale factor of the universe. So the evolution of the scale factor for some generic cases are given here. K, there is a parameter K sitting in that metric. It is called the scalar curvature. So it can be 0 for what is called a flat Euclidean type universe, -1 for a hyperbolic universe, and +1 for a positively curved universe. So if the universe is positively curved, it means gravitation dominates. So even though it starts out with an expansion, due to the attraction of the matter component in the universe, this expansion slows down and eventually it can be pulled back. It can become a contraction. So you get the bottom curve where the scale factor increases and then decreases. Now, if things are balanced, K is equal to 0, the energy of expansion and the energy for contraction, the gravitational potential energies, they are sort of balanced. What will happen is the universe can expand, but the expansion will become slower and slower and slower till the velocity goes to 0 at infinite separations. It is like you are throwing a stone up. If the velocity, kinetic energy is below that needed for escape, the stone will come back. If it is just at the escape velocity, it will go to infinity and its velocity will become 0 at infinity. If the velocity is more than the escape velocity, even at infinity, there will be a finite expansion rate. That is the smooth part of what is happening. Now, what happens if you have matter component, everything is homogeneous, everything is smooth, but suppose you have small fluctuations, small overdensities here and there. Gravitation is attractive. So if you have an overdensity somewhere, its magnitude will keep increasing. It will draw matter from the surroundings and it will grow the overdensity. So the evolution of matter perturbations in the formalism for treating and determining the evolution of matter perturbations in the universe was set up by P.J.E. Peebles, and you know that he got the Nobel Prize for it very recently. But if we look at this scenario, which comes from general theory of relativity, there is a problem associated with this. Now, if you come and look at the plot, there is this small square sort of thing written, plotted there. It shows cosmic time and how much the scale factor has grown by now. Now, if we run the universe backward in time, all these three curves are almost coincident. And at the beginning, very beginning, there is very, very, very little difference between all three. Now, what do we observe now? The present day universe. The present day universe, if you look at it, is behaving as though it is very close to a flat universe. Now, if it is very close to behaving very close to like a flat universe now, it must have been extraordinarily, infinitesimally close to a flat universe in the distant past. Then that kind of small difference between the flat universe is difficult to understand. So the universe must have started out as a flat universe. So, but why? Why was that condition chosen? Next, another problem is, this is called the fine-tuning problem. Why is it so close to flat? Another problem is what is called the horizon problem. That, to understand that, we have to look at one observation. So let me see. Oh, yeah, here is the observation. Now we can check the presence of matter by means of looking at the light from galaxies. Now, people who were experimenting in Bell Labs with radio antennas discovered radiation that was coming uniformly from any and every direction they looked at. So if it is something which is uniform all over the sky, it must be associated with the whole universe. Like, you go to your kitchen, there will be a room temperature, but the stove will be hotter. The fact that the stove is hotter doesn't mean the whole room is the same temperature, right? So you have the room temperature. Like that, you have the galaxies, they are sitting in the universe, and the universe has a radiation bath of its own, and that the temperature of that. So these lots of microwave observations were made. These radiations, the Planck the Wien's displacement law, etc. So they found that the universe is filled. Wherever you look, you can see black body radiation at some 2.73 Kelvin coming at you. Since it's uniform all over, you understand that it is associated with the universe. So you have this radiation component which we notice, and this is a distribution of that radiation component across the sky. Let us go back to the other slide. So that brings us to the horizon problem. So if the sky is looking so uniformly bright all round to us, everywhere you look, it's approximately just 2.73 Kelvin. Now, for any physical system to attain uniform temperature, the heat must have been conducted across the thing so that, uniformity resulted. Now, signals can travel, maximum speed is the speed of light. Now, in the time, this is the, I told you when we are looking far away into the sky, we are seeing the past of the universe. So when we are seeing the microwave radiation, this comes from a period when the universe was very, very young. So at the time when the universe was very, very young, the scale factor was extremely small. And its age of the universe was small, and if you look at the size of the region across which light could have traveled by the age of the universe when the background radiation, which we see now at 2.73 Kelvin, came into existence or started freely moving, we find that the patch C into that time will be only a small region in the sky now, but the whole sky is uniformly bright. That is called the horizon problem. So why is the cosmic microwave background uniform in temperature all over wherever we look? Given that signals, it cannot uniformize at a speed that is faster than the speed of light. These two problems were solved by postulating something called the inflationary universe, not just a Big Bang. You need what is called an inflation. Inflation means an extraordinarily rapid increase in the scale factor. So the earlier curves started, nicely, went up, off like that. Now you see there is a point of time when everything starts. Something like 10 to the minus 31 or so seconds later, there is a sudden exponential expansion, some e raised to 60 times the scale factor undergoes an expansion. So that is extremely rapid. And what happens is, if the small patches across which light could travel and everything could uniformize, they were expanded to enormous sizes in this inflation. So, if you take a circle and expand it enormously, each small portion of the circle will look like a straight line. Also, you have taken a small uniform patch and expanded it enormously. And we are living inside that small patch, and that small patch is so large that light traveling from outside that patch has not started reaching us yet. So wherever we look, we will see only uniformity. Thus, this idea of inflation solved the flatness problem as well as the horizon problem. So that is an important concept which we accept now as for our currently accepted model for the universe. Everything is current. Depending on evidence, we change our model suitably to accept what we discover from our observations. So currently accepted model involves this inflation. So you have these various phases of the universe, which we will discuss later. You start with, as the universe expands, it cools down also, because the number density of photons decreases, as well as the wavelength of the photons gets stretched as space expands. So energy of a photon is h nu. So the radiation cools down, but it keeps its blackbody spectrum nature. We need to understand more about what the components of the universe are before we start on how come the universe is looking like what it is looking like now. We don't see uniformity in matter distribution. We see them clumped into galaxies. So why? How come? How did this happen? Let us look at this. Let's look at the contents of the universe before we go into the fluctuations. We are talking about the smooth component only till now. So you have Big Bang, you have inflation. Now let us take a look at the contents of the universe. We talked about ordinary matter, which we are familiar with, stellar spectra, same type of absorption lines, emission lines, etc. you see, or in any galaxy or bright object which you see in the sky. But you see galaxies, wherever you see galaxies, so they must be stable structures, they must be in equilibrium. Gravitation is always attractive, so something must be countering gravity. Let's take a spiral galaxy, for example. Centrifugal force is countering gravity. So at various distances from the center of the galaxy, you can determine the rotational speed of the galaxy by again using Doppler effect. Spectral lines will be shifted, delta lambda by lambda give you the radial component. So what is expected is, when you go farther and farther away from the bright glowing mass of the galaxy, the distance is increasing, but mass is not increasing very much. So we are balancing G, mass inside R, into mass of the rotating object divided by R square, with mass of the rotating object into velocity of the object which is sitting at distance R divided by the distance R. What we expect is small m cancels on either side. What we expect is the velocity, which goes as root of G into mass inside R divided by R, to decrease as R increases very much, because m of R is not increasing very much. But you can see the observations there. The curve is not coming down. The curve is continuing to rise, and after some time it flattens. So what does it mean? There must be some unseen matter which is sitting there. That is the only way we can explain it from our known ideas about physics. So we postulate something called dark matter to be sitting there, associated with galaxies, and the visible matter is only a very small proportion, which is sitting in the deep potential well of this dark matter distribution. So we have dark matter enters as a constituent of the universe. Now, I told you we can track distances in the universe by using supernovae, for example. And supernovae, they don't occur alone, they sit inside galaxies. So supernovae will give you the distance to the galaxy. You take the galaxy, it takes a spectrum of light from it, which is the combined light of all the stars in it. You can find spectral lines. You can see to slow down as we see closer objects. So when we look at farther objects, the expansion velocity should be larger. So the Hubble constant as a function of distance, which is time, as we know, we are looking into the past, should reflect this expectation. But with supernovae, people looked at further and further galaxies, that is in the past of the universe, and compared the Hubble constant then with the Hubble parameter then with the Hubble parameter now, and what they find is that the expansion of the universe is accelerating. Now that is amazing. All the matter and energy we know, because E equal to mc squared, energy and matter behave identically in their gravitating properties. All that we know, and pressure is 1/3 the energy density, is connected to energy density. So that is also, its gravitational effect is always attractive. Then what is causing this accelerated expansion? So we had to postulate because of observations, we had to postulate something called dark energy, which exerts negative pressure so that there is a sort of repulsion and there is an acceleration for the universe. We don't know what it is comprised of. So we track these are the constituents we track. This is Hubble Ultra Deep Field, black body, Big Bang plus 800 million years. So old galaxies are also seen there. So there have been galaxies since 800 million years, when the universe was 800 million years old. Now, if you look at the distribution of the intensity in the radiation, you find that there are small fluctuations in the temperature. That is what are plotted on this axis. The reddish looking regions are higher temperature than the mean, and the bluish looking regions are lower to colder than the mean. The mean is around 2.73 Kelvin. So our objective in cosmology is to explain this observation of these inhomogeneities, their distribution at Big Bang plus 380,000 years. This is the distribution of fluctuations in the universe. And Big Bang plus 800 million years, by that time, all the matter had, sort of come together into galaxies. That is giving you how the universe, the fluctuations in the universe was behaving as a function of time. It gives you a clue to track it. I have written in below small SGWB. That means the stochastic gravitational wave background. So galaxies show you the matter fluctuations. The CMBR shows you fluctuations in the radiation distribution. The stochastic gravitational wave background is supposed to show you the fluctuations in the metric of the space-time of the universe, but not yet observed. People but work on it, trying to see what it could be like. So these are fluctuations. So primordial fluctuations, density variations, seeds of all the structures we find in the universe. Because we don't find a smooth uniformity, we find uniformity only in the average. So how did these structures form? So you write down your theory, you track the evolution of fluctuations in the radiation, you track the evolution of the fluctuations in the matter. Now when early universe was extremely hot, when the temperature increases as the scale factor decreases in inverse proportion. So in a hot universe, matter is ionized. Charges, electrons are strongly coupled to radiation by Thomson scattering. So radiation and matter move together. Matter fluctuations cannot grow by gravitation because it is tied to the radiation, which is always moving. And matter perturbations can grow only when the universe has cooled so that the temperature is low. Ionization, the electrons and the proton can come together and form neutral matter. This neutral matter So the fluctuations in radiation which you see, delta T by T of the cosmic microwave background is only of the order of 10 to the minus 5. While the density perturbations in matter, that is galaxies, they are of the order of 10 to the 3 is the density perturbation corresponding to a galaxy over the mean density, which you notice now. So how did a fluctuation in 10 to the minus 5 become a fluctuation in matter of 10 to the 3? So for that, dark matter helps us, because dark matter is not tied to the radiation. Dark matter potential wells can grow from the bare form beginning of the fluctuations themselves. Once they are inside the horizon, they can grow because they are in causal communication. Light can travel across the fluctuation within the age of the universe. They start growing by accumulating. So dark matter potential wells accumulate. Ordinary matter falls into it once they are free of the radiation, and that can happen when the radiation has sufficiently cooled. So once radiation and matter decouple, the radiation moves freely, and that is the radiation we see as the cosmic microwave background, carrying the imprint of matter fluctuations at the period when the radiation and the matter decoupled, 10 to the minus 5 order. So these fluctuations, they are quantum fluctuations of what is called the inflaton field. The particles whose field, we have photons, we have a collection of photons, we call it the electromagnetic field, like that. You have inflatons, we have a huge collection of inflatons, it's the inflaton field. So the quantum fluctuations of the inflaton field, the same field which caused the inflation, we don't know what the inflaton field is. We know ordinary matter only, we don't know dark matter, we don't know dark energy, we don't know inflaton. But we know that theoretically, some scalar fields can produce this kind of inflation. And we also, like at MG University, along with Dr. Rakhi, who is now at NSS College Pantalam, we also had proposed a type of interaction between condensed fermions, which can produce inflation. So the point about inflation, which I would like to mention here, is there are a huge variety of fields and situations which can give rise to inflation. We don't know which is correct. So what do we do next in theory? So this is one line of theory which is strongly, lots of people working on it, trying to cause inflation. Not just inflation, you can't stop at inflation because we have late time acceleration also. We see the universe is accelerating now. Earlier it wasn't, now it is accelerating in its expansion. So you have to figure out, what is causing this? And right now we have only theory to look at it. So there are a lot of theoretical models trying to explain, find fields which will cause inflation, early and late time acceleration. So, and you have to look at what happens to the fluctuations. You postulate a certain kind of field causing a certain level of inflation, etc. You have to figure out, what happens to the fluctuations. Because the fluctuations produce the later structure. Now, how do you analyze fluctuations? You use something called the power spectrum. So the fluctuations, you think it's a function all over space, f of xt, where x is x, y, z, let us say if you're using x, y, z coordinates. So if you're looking at the density field, it's a function of x, y, z, t. So you can take the Fourier transform. It will give you write the function in terms of amplitudes of sine and cosine waves. The power spectrum, if you think of an electrical signal, for example, which is a current as a function of time, the power delivered by the wave of given frequency versus the frequency. In general signal, you think of it as made up of waves of various frequencies. Now you can determine the power spectrum as the Fourier transform of two-point correlation function. Now the Fourier transform is only one kind of transform which you can do. Given a function, you can express it in terms of eigenfunctions of Hermitian operators, like spherical harmonics. You have eigenfunctions of the angular part of the Laplacian can be used to express the distribution of the cosmic microwave background, temperature distribution of cosmic microwave background in the sky. You can use spherical harmonics, take YLM theta phi are the spherical harmonics, find the power spectrum, average over the various m values which run from minus L to plus L. This is the power in the temperature fluctuations versus the angular scale. So you see that there is a huge amount of power sitting at a particular angular scale, which means strong fluctuations with to think sine waves of that scales, big density, then another big density, another big density. So at the time of the when the microwave background started freely, moving, decoupled from the radiation, this angular scale at that time corresponds now to 500 million light years now. So these fluctuations maxima were separated by 500 million light years. Now this produced what are called baryon acoustic oscillations in the distribution of galaxies now. That is, if you look at the galaxy distribution, you look at one galaxy, the probability for finding another galaxy at 500 million light years is very, very high. This is called the baryon acoustic oscillation, which can be connected to this peak, large peak in the angular power spectrum of the cosmic microwave background radiation. So you see, you can track the behavior of fluctuations using galaxies and their distribution, and you can track it by correctly and precisely observing the radiation part. We still haven't started observing using gravitational waves, so stochastic gravitational wave background is something else. So putting all sorts of observations regarding the universe together, how much of helium by mass, how much of fraction of deuterium by mass, when did the fluctuations in the CMBR, the redshift of CMBR, the galaxy formation redshifts, the 2-point correlation function of galaxies, the angular correlation function of the Planck spectrum, all sorts of things have to be brought together and behave correctly in the model which you set up. So we don't have a model which comes from first principles. We put in dark matter, we put in dark energy in various fractions, and we get a model which is in accord with observations. It's called the concordance model of cosmology. You can read it up very easily. Wikipedia will tell you. And then we have bouncing cosmological models, which, because you have in the general theory of relativity, the Friedmann equations gave you solutions which are singular. It started with radius 0, where density will go to infinity, etc., etc. So you think quantum gravity effects will intervene as you go closer and closer to the beginning. So instead of going to 0, you have the uncertainty principle, and you cannot go to 0 size. So universe must have decreased in size and bounced off from some finite sort of radius and come. So you have bouncing cosmological models which can sort of track using whether the fluctuations are Gaussian, non-Gaussianity in the fluctuations. Gaussianness is what you normally expect. If there are multiple fields causing inflation, then it can produce non-Gaussianity. So bispectrum means not 2-point correlation function. You look at the 3-point correlation function of the fluctuations. You can track the non-Gaussianity. So it might be giving you a window into the quantum gravity phase, what is called the pre-Planckian phase of what is called the pre-Planckian phase of the universe. That is, gravity is not quantized phase. That is the phase we are in now. You can go you have to go to what are called the Planck scales, extremely short times, 10 to the minus 41, something, I think. And Planck times for the effects of quantum gravity to be important in cosmology. So maybe these fluctuations could be giving us a glimpse into even that quantum gravity phases. So that is where astronomy gives us windows into fundamental physics that it's very, very difficult to get till now in the laboratory, CERN, etc., for example. So astronomy gave us oscillating neutrinos, which challenges the standard model of particle physics. It gives us this glimpse into quantum gravity, possible phases, phases where quantum gravity is important, even while experimentally it is very difficult to reach such, scales or such energy scales for exploration. So we have this Hubble tension, the Hubble parameter, V is equal to HD, that constant, its value now as determined from Planck, those fluctuations evolved using what is called the lambda CDM cosmological model is 67 only, determined like that. But if you look at variable stars plus supernovae plus the Doppler effect, you get 76.8 kilometer per second. So this disparity is a heavy matter of research in cosmology. There are various groups which are working on these things. Now we come to this slide. PBHs are primordial black holes. So if there are extremely strong fluctuations in the matter field, such large fluctuations that it's so dense, it will collapse and become a black hole. You can get what are called the primordial black holes. So all will depend on the behavior of the fluctuations and their evolution through the inflation. And secondary gravitational waves. There can be fluctuations in the space-time. Those are called the stochastic gravitational wave background. So due to the behavior of these fluctuations, the matter perturbations are called scalar fluctuations because density is a scalar. Gravitational wave, the space-time fluctuations are called tensor fluctuations because the metric is a tensor, the curvature, that is a tensor, described by a tensor. So ultra slow roll inflation. Inflation is supposed to take place because the inflaton field, during a phase when the inflaton field is evolving very, 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 very slowly with respect to time. It's supposed to roll down a potential. During that time, this inflation is supposed to happen. So ultra slow roll, and it's extremely slow and it is punctuated inflation. So instead of gradually and monotonically going to a potential minimum, it pauses in between. So that introduces a feature into the fluctuations of the inflation field. So can these ultra slow roll and punctuated fluctuation introduce secondary gravitational waves and primordial black holes is the question that was addressed by this Mr. Raghavendra in his seminar. Why are people looking at all these things? Because they're gearing up for the next level of the LIGO observatory. Observations are telling us what is the gravitational wave background. So we have to be prepared with theory to interpret the observation. Which theory will match the observation? So these are also research, kind of research activities which are going on. I've just indicated some of these activities, these things, scalar modes, tensor modes, all these things. You can easily read up Wikipedia and study all these things. I have just tried to give a flavor. The Press-Schechter formalism, for example, given a field of fluctuations, it tells you, you take some region. Will that region collapse or not? For that, you use what is called the Press-Schechter formalism. This Rubin Observatory, it's large synoptic survey telescope. It will give you very faint galaxies, so very far away, with tracking them. Every few weeks you go and look at the galaxy. Has a supernova gone off? What has changed? Etc. etc. So this will allow you to track the matter fluctuations in extreme detail. And here is the square kilometer array, the biggest radio telescope ever planned, which is coming up, going into the building phase. This will look at cosmic dawn, just at the period when the first stars and galaxies are forming. So instead of, these are forming galaxies, not already formed galaxies. So LSST will look at formed galaxies. This looks at cosmic dawn when the first stars and galaxies. So this scale will explore a period of the universe which is between the era of galaxies and the cosmic microwave background radiation. So it will allow you to track what is happening to the universe much better and maybe resolve the Hubble tension. So all these unknown things are remaining about the universe, just like people trying with the Ptolemaic model for planetary motion, cycles and epicycles, and you introduce this, you introduce that to try and understand. But then came Tycho Brahe's observations, and then Kepler went and worked on that data. And he said, this is not cycles and epicycles. Let us think of elliptical orbits with the sun at one focus. So that is the sort of phase cosmology is in now. But these are the mathematical, the experimental, observational, instrumental, etc. techniques which we use to do research in cosmology. Thank you so much.
Thank you so much, teacher, for the wonderful session. Now, if you have any questions, you can have it now.
I forgot to speak about this picture. The simulations are also used to understand what is happening to the fluctuations in the universe. You put in dark matter, you put in dark energy, you put in appropriate expansion corresponding to the smooth behavior of the cosmological model, and see what happens to the luminous matter. So this is a picture from one such simulation. So if you put in these ingredients in this proportions, what will the observed universe look now? That is another way of tracking, a very important way of tracking what is happening to the universe and trying to understand the universe. Okay.
Now the session is open for any questions. മലയാളത്തിൽ നിങ്ങൾക്ക് ക്വസ്റ്റ്യൻ ചോദിക്കാം കേട്ടോ. ഇംഗ്ലീഷ് പറഞ്ഞെന്ന് വെച്ച് ചോദിക്കാതിരിക്കണ്ട. എല്ലാവർക്കും ഒത്തിരി ഇൻട്രസ്റ്റ് ഉള്ള സബ്ജക്റ്റ് എന്നുള്ള നിലയ്ക്കാണല്ലോ നമ്മൾ ഈ സെഷൻസ് എല്ലാം ഹാൻഡിൽ ചെയ്യുന്നത്. അപ്പം നിങ്ങളുടെ കാര്യങ്ങൾ നിങ്ങൾ നേരിട്ട് മിസ്സിനോട് ചോദിച്ചോളൂ.
So I have a question. So if like what you showed in the last picture, since we don't have much information about the nature of this dark matter, I mean numerically how we put something for a simulation purpose. But I'm asking, if I had to put some numbers, some properties, how would people do that?
Okay. One thing is, it's the gravitational effects are being tracked, among other effects, of course. In the case of dark matter, it will have gravitational effects, but it will not suffer dissipation, the dark matter particles. In the case of matter particles, you have to think of, they can suffer dissipation. If they come too close together, they can stick together because their kinetic energy can be dissipated in gas interactions. Plus, the ordinary matter particles can, if their density passes a certain threshold, this can collapse. While dark matter particles are not like that. It is lambda CDM cosmology. So cold dark matter, they are moving with certain speeds. They are capable of condensing, but not to the extent that ordinary matter can. Ordinary matter can lose a lot of energy because in gas interactions. So they stick together. The dark matter particles are not considered to stick together. They do condense, but you avoid them sticking together. So you can mimic the behaviors.
Okay, thank you.
Okay, any more questions? Arshal, Sajad.
The topic was a very tough one. So,
That is the reason why, ma'am.
yeah. And I didn't avoid the mathematics because generally students don't realize how much goes into, each of these research programs. So quite a huge amount of what they study, they're all things which they study. Like, for example, the eigenfunctions of Hermitian operators, they study. But when it comes to thinking that, okay, something described as the function of two angles in the sky and writing them in terms of eigenfunctions of the spherical harmonic operator. So it's an application of what you study in mathematical physics. So quite a huge amount of application has suddenly been presented. I I presented it like that because that's what is happening in cosmology now. So all students who are thinking of doing research in cosmology, uh, uh, learn mathematical physics, learn how to apply it also. Generally, when we study to write an exam, but how to apply it to an actual research problem. So that comes in. And then I wrote statistics. So in all these data taking, you can never make perfect data. There are always errors input. So how reliable are your results? So there are confidence limits, confidence intervals to be determined. What kind of error? What is the statistics of the error which we are making? So immense amount of analysis goes in, even just to think of the error analysis itself. Then comes the instrumentation. These are extraordinary instruments which require hundreds and thousands of engineers, for example. The LIGO, for example, you have umpteen scientists putting out a LIGO paper, but you need umpteen engineers also to run LIGO. Because it's an engineering marvel, not just a scientific marvel. So, huge amount of superfine instrumentation. You might have been hearing about squeezed light, quantum phases of light which you can use for comes in precision metrology. That's the kind of stuff which is going on in gravitational waves. So these are extremely complicated instrumentational issues that have to be addressed, that has to be solved before you can make these observations. Then data analysis. These are petabytes of data which are coming in, the LSST or the SKA, how to transmit that data, how to store that data, how to condense the data and bring out some, products which require lesser memory, how to draw out the physical signal which is sitting in the data. All these things go in. And then you have to use artificial intelligence. And if you know human being can sit and work with petabytes of data and sort it out and get out the scientific information which is sitting there. So huge amounts of artificial intelligence. So it's not just physics, it's physics plus mathematics. Then you have to use physics, common sense from physics. Then you have to really use your imagination. Why aren't these things matching? You have put in all the physics you know, you have tried to make the best observations possible, and things don't match. So then you have to start and really think up, really imaginative solution to try and find out what is happening. So that is where the imagination enters. And I didn't mention that string theory also comes in here, because our best hope for trying to quantize gravity sits in string theory. So various weak field limits, or when you take various parameters, expansions and various parameters, those equations of string theory or insights from string theory can be used to understand the pre-Planckian universe, and that the influence of those on the fluctuations in the inflaton field. So from theoretical side also, cosmology is providing you a window into completely unknown territory. So field theory, it's good to know that you need to know a lot of things.
Okay, ma'am, that was a good message to the students actually. Because having an interest in cosmology, having an interest in cosmology or astrophysics is a different thing, because they have a very strong background in mathematics. That was a very
madam.
To have yes. Now, ma'am, I have another question. Can you please have a small discussion on what is alternate cosmology?
Alternate cosmology. Hello?
Yes, miss.
Please continue.
Alternative cosmology.
Hello.
Hello. As per Newton's first law, because the velocity is too much as എന്താണ് സർക്കുലർ മോഷൻ എന്ന് പറയുന്നത്? നടുക്കോട്ടുള്ള ഫോഴ്സ് ഈ സ്ട്രേറ്റ് ലൈനിൽ ഫസ്റ്റ് ലോ അനുസരിച്ച്
നടക്കുന്നു. മാസിനെ നമ്മൾ എങ്ങനെയാണ് പഠിക്കുന്നത്? എങ്ങനെ ഫോം ചെയ്തു?
ഓക്കെ, സ്പീഡ് ഓഫ് ലെറ്റൽസ് ട്രാവലിംഗ് അറൌണ്ട് ടൈമിന്റെ എന്ന് പറഞ്ഞ കോർഡിനേറ്റ്സിൽ എഴുതിയാൽ 1 - 1 - 1 എന്നുള്ള 4x4 മാട്രിക്സ്, ബാക്കി എലിമെന്റ്സ് 0 ആയിട്ട് എഴുതാം. ഓൾ എലിമെന്റ്സ് ലോ വാല്യൂ ഫോർ ദ ഒരു ഫ്ലക്ച്വേഷൻസ് ഡിറ്റക്ട് ചെയ്യാൻ തുടങ്ങിയിട്ടില്ല. സ്പേസ് ടൈമിനെ പിടിച്ചുലയ്ക്കാൻ ഭയങ്കര പാടാണ്. ലൈക്ക് ഐ ടോൾഡ് യു, ക്വാർട്ടർ പോൾ മൊമെന്റിന്റെ തേർഡ് ഡെറിവേറ്റീവ് ഡിവൈഡഡ് ബൈ C⁵5 ഇരിപ്പുണ്ട്. അതിന്റെ പവർ റേഡിയേറ്റഡ് എന്ന് വെച്ചാൽ എനർജി റേഡിയേറ്റഡ് പെർ യൂണിറ്റ് ടൈമിൽ. So to produce a small fluctuation, you need immense changes in quarter pole moment, aren't it? So ആ വേവുകളെ നമ്മൾ ഡിറ്റക്ട് ചെയ്യാൻ തുടങ്ങിയിട്ടില്ല, തിയറിറ്റിക്കലി ഇൻവെസ്റ്റിഗേറ്റ് ചെയ്യാൻ തുടങ്ങിയിട്ടുണ്ട്. ബിക്കോസ് ലൈഗോ വരുമ്പോഴത്തേക്കും തിയറിറ്റിക്കൽ ഇൻവെസ്റ്റിഗേഷൻസ് ഇങ്ങനെയാണെങ്കിൽ ദിസ് ഈസ് ദ കൈൻഡ് ഓഫ് സ്പെക്ട്രം എന്ന് വെച്ചാൽ ഇന്ന ഫ്രീക്വൻസിയിൽ ഇത്ര ആംപ്ലിറ്റ്യൂഡുള്ള വേവ് ആണ് എന്നുള്ളത് നമ്മൾ പഠിച്ചു വെക്കുകയാണ്. So that when the results come, then find out, okay, which theory matches with observations. That is how you do it. You need to know a lot of tensor analysis and a lot of field theory, etc., to work in gravitational waves. Like mathematics. Is that okay? Is that okay?
Okay, thank you.
ഹലോ മാം. ഹലോ, കേൾക്കുന്നുണ്ടോ? മാം, എന്റെ സംശയം ഡാർക്ക് എനർജി ആയിട്ട് ബന്ധപ്പെട്ടുള്ള ഒരു കാര്യമാണ്. ശരിക്കും നമ്മൾ സ്പീക്കിംഗ് എത്ര കോൺഫിഡൻസോട് ഡാർക്ക് എനർജി എന്ന് പറഞ്ഞത് പോസ്റ്റുലേറ്റ് ചെയ്യുന്നതിന്റെ
should go and look up is cosmology.
Yes.
So it is from their observations that we figure that the universe is in an accelerating phase in time phase. Otherwise, have published the results and so at least 3
ചെയ്തിരുന്ന സാമ്പിൾ സൈസ് വളരെ കുറവായിരുന്നു എന്നുള്ളത് ഞാനൊരു സൂപ്പർവൈസൽ റീഡിങ്ങിലാണ് കണ്ടത്. ഒരു സാമ്പിൾ സൈസ് കുറവാണെന്നും പിന്നെ ആളുകൾ അതിലേക്ക് കൂടുതലായിട്ട് ഇങ്ങനെ ഒരു ചോദ്യം ചോദിക്കാൻ കാരണം. അപ്പൊ അത് എത്രത്തോളം ശരിയാണെന്നുള്ളത് ഒരു ഇത് പോസ്റ്റുലേറ്റ് ചെയ്യേണ്ടി വരുന്നുള്ളതിൽ ഇപ്പോഴും അതൊരു സംശയത്തിൽ കിടക്കണം.
ഒബ്സർവേഷണൽ റിസൾട്ടിലാണ് നമ്മൾ ഡാർക്ക് എനർജി പോസ്റ്റുലേറ്റ് ചെയ്യേണ്ടി വരുന്നത് ആ റിസൾട്ട് മനസ്സിലാക്കാനാണ്. നോബൽ പ്രൈസ് ഈസ് അവാർഡഡ് ഓൺലി ടു എക്സ്പെരിമെന്റ്. ഇപ്പൊ റോജർ പെൻറോസിന്റെ കൊടുക്കുന്നത് കാരണം അന്ന് കൺഫർമേഷൻ വേണ്ടി വന്നു. യു കൻ റൈറ്റ് എ ലോട്ട് ഓഫ് മാത്തമാറ്റിക്സ് ബട്ട് ഡസ് ഇറ്റ് മാച്ച് വിത്ത് ഒബ്സർവേഷൻ? ഈസ് യുവർ ഫിസിക്കൽ ഇൻസൈറ്റ്, was it good enough to hit the right model for what is happening, or to give the right insight? That is the step. That can be answered on observations.
Okay.
Although neutrino oscillations were Majorana neutrinos, they have been around since so long. Nobel Prize, eppozhana Nobel Prize poyathu? So when the neutrino oscillations were experimentally detected, they set up an experiment which could, capture it. Apparana Nobel Prize. Otherwise, you can write a lot of theories. There are thousands of.
Okay, thank you.
Yeah.
Any more questions? Hope there is no more Dr.K.Indulekha ma'am. Platform as well as in the YouTube streaming personality before us for this afternoon. Ma'am from State Higher Education Council has joined us. So we feel this forum has its meaning now, and we will be having such light in all our future endeavors. Thank you, ma'am, once again.
Yeah, I know there were school students. Otherwise, I would have put in chunks which are more suitable for them.
Only 2 or 3 school students. 2 or 3 school students were there. Majority were college students. School students joined out of their sheer interest in this area. That's right.
That's nice. Very nice. Bye.
So we have come to the end.
Bye.
Bye, ma'am. Bye, ma'am.
Yeah.
So we have come to the end of the session. I guess in all of your endeavors, there are live sessions coming.